Okay, so far we have ignored friction, and that's what this video is about. So friction is a force that resists the relative sliding motion of solid surfaces and or fluid layers moving relative to one another. Now, we're not going to worry so much about the fluid layers right now, but mainly we're going to focus on solid against solid friction. And we're going to consider how that is when two solids move relative to one another. So we want to understand how friction behaves. And so the first thing that we want to know is that friction is always directed to oppose any relative motion, i.e. sliding. So if I've got a block here sitting on the floor, I attach a rope, I start pulling the block to the side, which way is the block going to move? It's going to start moving to the right. And so even if the friction is strong enough to hold it in place, you could imagine that the only way that this force could make this block move is to the right, and so the friction is going to be to the left. Now, what's going to happen at first, if you start the force at 0 and you slowly ramp it up, what's going to happen is the friction is going to match the force. So you can imagine you're pushing against a refrigerator or trying to pull something really heavy. It doesn't move, but so you pull harder and harder. Eventually you overcome the friction and it'll start to slide across the floor. So what does friction depend on? Friction depends on two things. It depends on how rough the surfaces are and how hard they're pressed together. The more you press a surface together, the bigger the friction is going to be, and the rougher the surfaces, the bigger the friction is going to be. That's why if you have smoother surfaces, they tend to give you less friction. Now, the direction of the friction, as I said, is always going to oppose the motion. So these are the two things. So the two things that friction depends on, the strength of friction depends on the roughness of the surfaces. And so that would be the surface here where they're in contact. Hopefully that's obvious. But the roughness where the two surfaces make contact, that's going to be one factor that the strength of friction depends on. And then how hard the surfaces are pressed together, that's the other thing that's going to affect how big the friction is. So we want to look at why roughness is a source of friction. And so I have a block sitting on the floor, and this inset here is magnifying this part right here. And you can see when you magnify it, you can see the block, and I've done the block in kind of a brown here. If you zoom in with like a microscope, you're going to start to see, if you zoom in enough, you'll see nooks and crannies. So what feels like a smooth surface is actually got nooks and crannies and hills and valleys, and you can see this surface is going to be rough when you zoom in. So no matter how smooth something feels, if you zoom in enough, you're going to see roughness. And so the nooks and crannies of the block and the nooks and crannies of the floor, they sort of overlap with one another. And you can kind of see, for example, right here, if I want to move the block this way, this nook here has to slide up this part of the floor, the little valley in the floor. And there's another spot right here that's going to catch, and another spot right here that's going to catch. And so this is why you can see the roughness impacts the amount of friction. And if you have more roughness, that means those little hills and valleys are going to be deeper. Now, here's something else that this model of friction explains. If I want to reduce the friction of, say, a moving part, like, say, a piston in an automobile engine, well, I might want to lubricate it with some kind of oil. Why does lubricating something with oil reduce the friction? Well, something like oil is going to be an incompressible fluid. It's not going to compress very much, no matter how heavy the thing sitting on it is. And so if you fill all these nooks and crannies with a fluid that's not compressible, the object is basically going to float over these nooks and crannies. And so that's why something like oil can actually reduce the friction between two surfaces. So the next thing I want to do is I want to write down an expression that gives me what I know about friction in terms of the parameters that the force of friction depends on. So I've got an equation, F is equal to mu times the normal force, F sub n. Now, if I have a floor here and I have a block, we've seen previously that the weight is going to be mg, and there's going to be the normal force. And what the normal force tells me is that that's basically the force that the floor is pushing back with. Now, if I come and push down with some extra force, the normal force is going to be the mg plus that extra force. And so basically, no matter what configuration you take, the normal force really tells you how hard the forces are pushing together, because that's how hard the floor, that's one of the two surfaces, that's how hard the floor has to push back with. And so by Newton's third law, you're going to have equal and opposite forces at those two surfaces. And so no matter how many total forces that you end up with, the normal force is going to be basically the amount of hardness with which the two forces are pressed together. And so that's one of the two things that the force of friction depends on. The other thing that the force of friction depends on is the coefficient of friction. And that basically is a numerical measure of how rough the surfaces is. And a bigger coefficient of friction means the surfaces are more rough. Now, usually in a problem, that's something that you're going to be given, or you'll be given everything else and you're going to be asked to determine what that is. And again, this, if you've never seen this symbol before, this is the Greek letter mu, and it looks like a cross between a U and an M, and it's a mu. And I sometimes write that out as MYU to kind of give you the idea how to say it, a mu. Anyway, that's the coefficient of friction. The next thing we want to look at is how does the force of friction respond when you apply a force to an object. So up in this little inset up here, I've got a block that's sitting on the floor, and I apply a force to it, and I start pulling as if to drag the block over to the right. Of course, we know the friction force is always going to act to oppose that motion. So if I start with zero force, and then I slowly start to pull, and I slowly pull harder and harder and harder, what's going to happen? This graph shows you what's going to happen. And so what this is I've got this in this kind of teal blue color here. This is the friction on the vertical axis, or the y-axis, and the applied force is on the horizontal axis. And so this force is the horizontal axis, the other force is friction, and I'm plotting the friction force versus the applied force. Now, so as I increase the applied force, the amount of friction force increases as well. Because as I'm increasing this, this block is not yet moving. I haven't produced enough force to overcome friction, so I'm slowly pulling with more and more force. The friction has to get stronger and stronger, because if this guy doesn't start accelerating yet, I know that this force and that force have to equal each other. And so that's what you can see. As I increase the force, the friction force matches the applied force until you get to some maximum friction value. And that's sometimes called Fs max. And the S stands for static. That means not moving. And this is the region where the block is not moving, and that's called the static region. So here, the friction force is getting bigger and bigger and bigger and bigger until it reaches its maximum possible value. And so this is the maximum value of the static friction. Once it starts to move, what we find experimentally is that the force of friction actually drops down precipitously. And so the force of friction drops down quite a lot, and then it's relatively constant. And this would be when the block, after the block has started sliding. And so whenever the block starts sliding, no matter how fast it's sliding, whether it's speeding up or slowing down, as long as it's sliding, the amount of friction that's applied is basically constant. And you can see the kinetic version of friction, and that's what the K stands for, by the way. So when it's sliding or moving, that's called the kinetic friction. When it's stationary, that's called the static friction. And so in the kinetic region, we have this constant force of friction. And you guys might have experienced this drop. If you've ever had to push anything like a refrigerator or a couch or something really heavy, what you'll find is you push harder and harder and harder, and then once it starts sliding, it's actually easier to keep going than it was to start moving in the first place, right? Hopefully you've experienced that before. And so that's what we see in this graph. You're increasing the applied force, the friction force is increasing to match it, you get to the maximum value of the static friction, then the block starts to slide, and the amount of friction force drops down quite a lot, and then it's constant as it's sliding. And so this kinetic friction is almost always going to be less than the maximum static friction, just as an FYI. So here are the cases, and I'm just going to kind of sketch in this graph again that we just saw. So I've got my friction force, little f, versus my applied force, big F, and as we go up to the Fs max, the friction of the static force is going to be less than the maximum friction of the static force. And so what that means is the friction right here, which I would read off the graph right there, is less than the maximum possible friction that I'd read there. Once I get to this, then the maximum static friction is equal to mu sub s times F sub n. And this mu sub s is called the coefficient of static friction. And again, that's just basically how rough the surfaces are. And so the coefficient of static friction is called mu sub s. We can look at the force of kinetic friction, and I just saw an error in my little equation here that I corrected. So I've corrected it, and so we have the force of kinetic friction is equal to mu sub k times the normal force. And what we can know is that that mu sub k, that's the coefficient of kinetic friction, which is this mu sub k right here. So here we have the force of kinetic friction equals to the coefficient of kinetic friction times the normal force. Now here I've sort of drawn our little model of friction depending on roughness again. I want to get over this idea that, or I want to explain this idea of why we see this drop. When the objects are sliding, why do you get less friction? So when the situation is static, and so they're not moving relative to each other, these little nooks and crannies, they act like little interlaced teeth, and if it's not moving, the full weight of this block is pushing them in together, and they kind of sink in as deep as possible. But once it starts moving, these guys are gliding on top of each other. They don't have time to fully sink in and fully engage. And so that's why the friction gets less when it's sliding. And so this model that we have of friction depending on roughness, that explains things like how lubrication works, like we've already talked about. And it also explains why you see this drop in the amount of friction when it's sliding versus when it's just sitting there. Okay, so let me recap. I've got a block. I apply a force to it in order to make the block slide across the floor. The friction is going to resist that. And so I have to pull harder and harder. The friction is going to match the amount of force that I'm pulling with until the friction gets to its maximum value. Then it starts to slide. Once it starts sliding, the friction reduces, but after that point, it remains constant. And so that's sort of the basics of how friction works.